All right, our first topic for today is heat of formation. The heat of formation is the values, typically speaking, they're the values we find in the chart. And when I say in the chart, I mean this guy. But there's a definition that you need to know. It is the amount of energy absorbed or released when 1 mole of a compound forms from its pure elements. I realize that's a little bit messy. I apologize for that. Key parts here: 1 mole and pure elements. So when I say pure elements, I mean, for example, Al or O2 if something's diatomic. To show you an example, let's say we're going to write the formation reaction for, first we're going to do K2O. So I'm forming K2O. So that means K2O goes on the right side of the equation. I'm going to make it from K and O. Oxygen is diatomic, so I'm going to put a 2 there. When I balance this reaction, I cannot add anything before the K2O. Because the definition is for 1 mole, that coefficient needs to stay a 1. So the way I'm going to balance the reaction is by adding coefficients, even if they're fractions, to other things. So for example, I'm going to balance the K's with that, and I can balance the O's with a 1/2. I'll show you another example. Let's say I'm writing it for HNO3. HNO3 is my product. I have 3 elements here: H, N, and O. Diatomic, diatomic, diatomic. Balancing, I'm going to need a 1/2, a 1/2, and a 3/2. I want you to try a couple and then pause it and then come back and check your answers. I want you to write it for Fe2O3, KBr, and H2SO4. So go ahead and pause and then come back and check your answers. All right. Iron is not diatomic. Oxygen is. Balancing, I'll need a 2 and a 3/2. KBr, K is not diatomic. Bromine is. I'll balance with a 1/2. H2SO4, hydrogen diatomic. Sulfur not. Oxygen diatomic. And that is balanced.